there are two types of charge you can get here. There's a positive charge and a negative charge. So if you put two negative charges together, you should actually get them to repel, so they push apart. And if you put opposites together, like a negative and a positive like this, then they should actually attract. All right? And you can show that two other like charges, two other positive ones, will also do the repulsion. So there's an experiment you can do to show that. And the experiment would be to charge up one of the rods, so the perspex rod there can be charged up, okay, and placed on some sort of a balance like that. You charge up another perspex rod with the same sort of charge then, so that these are both charged positively. As they get near each other, they too will repel. You should be able to see they push apart. You should be able to get that to slow down as well and go the other way. So like positive charges here are actually repelling each other, okay? And if you get the opposite charge there, so bringing the ebonite one, this black rubber, which gets a negative charge when you rub it with fur, that will actually cause it to attract, because opposites attract. And you can do the same thing with two negative ebonite rods, okay? So why would the actual rod become charged when you rub it with the fur? If you've got the rod there, and it happens to be a perspex rod, and it is rubbed with your fur, rub it with fur like this, if it becomes positively charged, how does that occur? Now you've got to remember that inside these are actually made up of multiple atoms, or many atoms. And inside the atom you've got a positive nucleus there, which has got protons inside it. And around the outside of that you've got the negative electrons going there. Okay, negative electrons. Now they're the ones that are moving at high speed, so they're the ones that are free to move. When you do rub materials together, it's possible to get the electrons to leave that and go on to something else. So in the case of this perspex rod, because it's become positively charged, it must be the negative electrons leaving the rod and going onto the fur. So the negative charge has actually left the rod and gone onto the fur like that. And that's left the actual positive charge behind. This is a positive 6 left behind here. It should be a negative 6 left over there because you've just created an imbalance of charge. Okay? You can get it to rub the other way around. So in the case of ebonite, which is that black rubber, that becomes charged negatively. And the reason for that is that when it rubs on the fur there, the electrons actually rubbed off the fur and onto the rod. So they move that way around. So that's based on the atoms there. So there's a few PowerPoints you can look at to do this here. So all materials are made of atoms which contain electrical charges, and that's a very simple one. Most of the materials we deal with have got a lot more protons than neutrons and electrons than this particular simple one, but it gives you the idea that electrons are moving at high speeds at a distance from the nucleus. They're the ones you can rub off due to friction, okay? And they've got the negative charge there. So it's always the negative charges that are going to move when you sort of transfer between solids, okay? Overall, an atom is normally neutral. There'll be an equal number of positive charges, equal number of negatives, and by rubbing with friction, what you actually do is move the electrons from one object to another. So you can do this by moving a cone through here and so on, all right? And you can get a build-up of this static charge, and it's called static because it means stationary or still, where it stays on the object. You can get a build-up if you sort of rub it for a while and transfer quite a few electrons from one object to another, okay? So it's all about the transfer of the material, which you can see in that comment there, due to friction, all right? One material ends up with more electrons, but gets a negative charge. The other will get the overall positive charge because it's missing electrons, and therefore it's got more of these positive protons in the substance than electrons, so it's got the extra positive charge. And the friction can be used to do that, okay? It works very well with insulators, by the way, so the extra electrons stay off there or on there. And if I show you some examples of this, we'll try the acetate, I think, first there. If you get the acetate there, if that is rubbed with the cloth, okay, like that, it turns out the electrons move off the rod onto the cloth. And you can see the rod's now left with excess of positive protons on the right, and it's gained negative electrons on the left. The blue ones have gone to the left there, so the extra blue ones there. If you count up on the fur there, or the cloth, there's more negative charge there. They used to use a gold leaf electroscope to actually measure how much static electricity was there. And what happens there is if you bring a negative rod to the top, the negative electrons in the top of that metal plate will be pushed down away from it because negative charges repel each other. And as the negatives collect at the bottom where the gold leaf was, they would repel, and you'd have a scale there to see how big the charge was. Okay, you can use a Van de Graaff generator as well. I've decided not to use this during this presentation because it does tend to make the screen flicker and go off. So I'll try and do one at a distance later on. But you get someone's hair to stand up by using the Van de Graaff generator. That gets charged up because the rubber belt gets rubbed past the friction. It loses its electrons, so the belt becomes positively charged, goes to the top of the Van de Graaff, positive charge collects there, and you can then actually use that positive charge on someone else. Actually, if it goes near an unearthed object, an earthed object, the charge will fly from that positive object to the earthed rod, and you'll see that movement of charge as a spark because the moving charges have energy, they light up the actual air, and it's that bluish colour you see in lightning as well. If an insulated person touches this same thing, they can collect that same charge. The charge goes on their hair, on the head, they get the same charge, and so your hair stands up. And you can see that as a result. So the force between charges is a quick recap. I'm just going to skip through some of these. If they're both the same charge, like these acetate rods, we expect them to actually repel each other and push apart. If they're actually opposite charges, like this positive one on the left and negative on the right overall, they should actually attract. I won't do that one there. So you could actually sort of do things with a balloon and actually rub it up. So let's see what happens if we rub a balloon on something, then bring it near a cat. So you can rub the balloon on a jumper there. I'll just rub it with my finger there. That rubs it and charges it up. Bring the balloon in the cat, it actually attracts the cat fur. Now why is that? Because if you haven't charged the cat fur, they're not in contact with each other. Why does the cat fur still move up? Catch the spot the balloon. When the actual charge, in this case the negative charge of the balloon, comes near the cat fur, the electrons in the cat fur are negative, the balloon is negative, they'll repel each other, so the negative electrons get pushed away from the tips of the cat fur. Now that leaves the cat fur positively charged, and that's near the negative charge of the balloon. They'll attract each other with quite a strong force because they're fairly close to each other, and overall it should actually cause the hair to stand up because of that attraction. And you can see that result there. The positive fur that's left behind there, the tips, is attracted more strongly to the balloon because it's closer than the negative charges which are further away now. And you can do the same thing with water, a stream of water or paper and so on. There are several uses of static electricity there. One's in photocopiers, laser printers, one's in doing the spray painting of cars. You charge one of them up positive or one of them negative so that the actual paint spray coming out is positively charged as it comes out the gun and it heads onto the metallic bodywork which is negative. You can also do it to actually remove factory smoke. You can charge up the smoke and get it to attract to the side and be deposited, or heart defibrillator. So we just look at one of these, the photocopier for example. The photocopier has that red drum there, which only conducts in the presence of light. So as a process, what you do then is you first of all charge the drum up using a very high voltage wire there, and that transfers some charge onto the actual drum by a corona discharge process, which we study in Year 12. Having charged the drum up, you then try to expose the drum with the actual object you're trying to take a photocopy of. So in this case here, it's the letter A up the top there. So a light will actually be taken across that letter, and you should see that happening in a photocopier. That light will reflect off the mirror through some lenses and be focused onto the drum, which is going to roll around at the same time. And you should see the drum being exposed by the white light bits of the paper. And where the bits are black, it will not become exposed, and so that will stay charged. The discharge only occurs where the white sections are. So you can see you've now got a positive drum for a letter A only. So we now need to get the toner or the ink onto that drum. So the toner is very fine powder particles, and that will be attracted to that drum and move across to it, okay, from the toner roller, which is one you have to replace when it runs out. So you've now got the toner or ink on the actual drum. You need to transfer it to the paper. How do you do that? You use static electricity again. So you put an even bigger charge on the paper using another wire, and that will transfer to the paper as it rolls underneath the drum there. It still isn't stuck to the paper at this stage because it's just that loose toner particles. So you could rub it off at this point if you wanted to. What you need to do is actually have a heat roller which will cement that onto there by heating it up and getting it to melt a bit. There's a bit of plastic involved in it as well as a material, and it melts onto there, and that's what comes out as a warm copy. When you first turn it on, that's what you wait for to heat up before you can use the photocopy. So that should give you some basic ideas. So as I said, there are other applications that you can use for that. The spray painting of the CAM one, for example, you attach that to a positive terminal and a negative terminal. So the car body goes to one terminal, in this case it's positive in my example here, and the spray paint nozzle, and therefore the spray paint comes out negative, and that attracts it to the body rather than letting it just floating in the air and going onto the side walls. It reduces that amount of sort of wastage. So just bear that in mind as well. I think that will be enough for now. So key points here to look at is you should be aware that static electricity means it's stationary, it stays still. There are two types of charge, positive and negative they call them. It was Benjamin Franklin that first coined that. The light charges will repel each other, as you can see here, and the opposite charge will attract. And when you bring a perspex rod up and actually charge the process, it charges because electrons are transferred off the rod in this case here. You can see the electrons being transferred off the rod. But an ebonite one, it's the opposite. You can actually get electrons transferring off the fur and onto the rod and giving them excess negatives here, and that's why the rod becomes negative and the extra positive left behind will make the fur positive. So that's enough on static electricity. Thank you.